Welcome to the final foundation lesson of our linear algebra explainer. We've spent so much time exploring how data moves and shapes itself, and honestly, you should really be proud of how far we've come. But today, we are tackling the absolute ultimate mathematical engine behind modern AI. It's called Singular Value Decomposition, or SVD. You can basically think of this as the universal matrix autopsy. Now, we've looked at eigendecomposition before, which is great, but it has this one fatal flaw, right? It really only works on perfectly square matrices. And let's be real, in the wild, most of our data is rectangular. So today, we're reaching the very top of the mountain. SVD works on literally any matrix: square, rectangular, invertible, singular, you name it. It isolates the core meaning and fundamental geometry of that data. It's essentially a mathematical scalpel that slices away the redundant noise to reveal what is truly essential. Section 1, the SVD factory, rounding the abstract in physical reality. Okay, to really wrap our heads around the weight of what SVD accomplishes, let's step totally away from the math for a second and imagine a bustling, massive food processing factory. We can break this whole operation down into 3 specific chambers. First up is the organizer. Picture this chaotic stream of raw ingredients flying down a conveyor belt. The organizer's only job is to rotate and line them all up perfectly. Then they head into chamber 2, the scaler. This is like a giant mixing board with independent volume knobs for every single organized stream. Some knobs are cranked all the way up for the crucial ingredients, while others are dialed way down. Finally, everything moves into the formatter, which takes those scaled streams and just rotates them into their final packaging. Now, the absolute secret weapon of this entire factory is that scaler chamber. Think about it. If you walk right up to that mixing board and turn the volume knobs all the way down to 0 on those barely used secondary ingredients, the final packaged meal is going to taste exactly the same. But suddenly, your factory is incredibly efficient. Well, SVD is the algorithm that tells you exactly which streams matter and which ones you can just completely ignore. Section 2, the anatomy of a matrix. From the physical factory to the mathematical abstract. What's genuinely amazing here is how our physical factory chambers map perfectly onto the core math. For any matrix A, there is this flawless factorization. A equals U times sigma times V transpose. This right here guarantees that any linear transformation can be perfectly dismantled. V transpose, that's our organizer, an orthogonal matrix rotating the input. Sigma is our scalar, the diagonal matrix holding our singular values, which are basically our volume knobs. And U is the formatter, another orthogonal matrix rotating everything into the final output space. If you want to visualize this, imagine applying a linear transformation to a perfect 2D unit circle. SVD breaks the whole morphing process down step by step. First, V transpose gives it a pure rotation so the axes naturally align. Then sigma stretches those axes out, maybe pulling the horizontal by 3 and the vertical by 0.5. Again, those are our volume knobs in action. And finally, U steps in to give it a final rotation into the output space, leaving us with an ellipse. Section 3, the Eckart-Young reveal, separating meaning from noise. So why do we care so deeply about isolating these singular values in the sigma matrix? Why even bother turning down those volume knobs? Well, that brings us to the Eckart-Young Theorem, and honestly, this is the dramatic centerpiece of our entire journey. This theorem provides hard mathematical proof that dropping the smallest singular values is the absolute best, most optimal way to compress data without destroying its true signal. It minimizes the error perfectly. Without this, compressing data would literally just be a blind guessing game. Let's make this super concrete. Imagine you're looking at a stunning, high-resolution digital image of a complex statue. It's perfectly sharp, you can see every tiny little detail, and that's because all of its singular values, every single volume knob, is currently active. But here is your aha moment. As you gradually turn off the small singular values, those tiny little volume knobs, the image starts getting a little blurry. It looks like static, but the second you add back just the top singular values, the loudest knobs, the image snaps right back into crystal clear focus. This proves exactly what Eckart-Young tells us. SVD is literally separating structural meaning from static noise. The top values are the actual statue. The tiny ones are just static. By truncating our matrix to what we call rank K, we isolate exactly how many of those top singular values we actually need to compress a massive dataset while keeping its core essence intact. We're tossing out the noise and preserving the true mathematical soul of the data. Section 4. SVD in modern AI, the mathematical engine behind today's models. Let's see how all this theory builds into the exact applied math that powers the AI you use every single day. Because SVD is absolutely everywhere. Whether we're fine-tuning a massive language model, stabilizing an image generator so it doesn't just spit out garbage, or predicting what show you're going to binge next on Netflix, SVD is the universal tool exposing the hidden geometry of all that data. Take large language models, for instance. Fine-tuning a massive model means updating a gigantic weight matrix. But a technique called LoRA, or low-rank adaptation, uses the exact principles of SVD. It parameterizes that massive weight update as the product of two tiny matrices. This forces the system to find a low-rank solution that mimics SVD, which saves an unbelievable amount of compute. We don't have to learn millions of redundant parameters, because SVD mathematically proved to us that most of them are just noise anyway. Or look at generative adversarial networks, or GANs. Training them can be notoriously unstable, so developers use something called spectral normalization. They literally take the single largest singular value, the biggest volume knob of them all, and divide the entire weight matrix by it. This elegant little constraint mathematically stops the network from amplifying gradients out of control. Section 5. Constraints and engineering fixes. Transitioning from pure theory to practical code. Now, as beautiful as this math is, actually running it on billions of parameters inside a computer is a whole different story. If you naively ask a program to run a full SVD on a giant matrix, you are going to walk right into some brutal traps. People constantly confuse the V matrix with V transpose. If you ask for full matrices, you can easily trigger catastrophic out-of-memory crashes by calculating totally useless null space vectors. And differentiating through SVD when singular values are close together, that causes division by zero, which completely crashes your neural network training with NAND losses. Plus, computing a full SVD takes immense time and memory. But the genius engineering fix here is randomized SVD. By using random projections, we compress the matrix into a smaller subspace before we even calculate the singular values. This completely sidesteps the computational bottleneck, bringing the time complexity way down and making modern AI analysis actually feasible. Thanks to this optimal rank K truncation technique, validated by Eckart-Young and optimized by randomized SVD, we can slash memory footprints by orders of magnitude. We're talking shrinking a 400 megabyte weight matrix down to just 1.2 megabytes without losing the structural meaning. That is exactly what makes running advanced AI locally on our phones and laptops a reality today. As we wrap up this foundational explainer together, I want to leave you with one big, inspiring frontier question. SVD is the absolute masterclass in linear transformations, but neural networks are fundamentally nonlinear. So how might future researchers adapt this flawless mathematical compression to conquer the nonlinear depths of tomorrow's AI architectures? It is such a fascinating problem to think about. Thank you so much for joining me on this journey, and keep exploring the incredible geometry hidden inside your data.